Alright guys, so welcome back. Today we're going to look at the examples in assignment number 5 in your notes packet. So this is really finally getting to the whole purpose of this chapter in this unit. Being able to look at calculations of chemical reactions that either start with a gas or end with a gas, so have a gas product or reactant, but don't necessarily happen at standard temperature and pressure. Okay? So we use standard temperature and pressure a lot early on because it really simplifies calculations. Okay? We can use 22.4 liters per mole and it makes our life a lot easier. However, in the real world and real chemistry, standard temperature and pressure rarely occurs. Okay? So what we'll do is slowly ease our way into dealing with calculations that don't necessarily have standard temperature and pressure conditions. Okay, so let's kind of just learn by doing here and look at a couple of examples together. So a sample of ethanol burns in O2 and CO2. So it's a simple combustion, or burns in O2 to form CO2 and H2O. So a simple combustion reaction. It gives you the reaction. It balances it for you. If the combustion uses 55.8 milliliters of oxygen, measured at 2.26 atmospheres, and it gives you the temperature, what volume of CO2 is produced when measured at STP? Okay, so there's a lot going on here. So let's kind of just try and break this problem apart and see what we got to do. So let's say that the mass of oxygen we're given. First, let's pretend we already have this mass of oxygen. If we already had the mass of oxygen, we could pretty easily convert from mass of oxygen to moles of CO2. But we don't have the mass of oxygen, and we really don't have an easy way to get there yet. So what we have to do is take the volume of oxygen and we want to somehow convert that to the number of moles of oxygen. Okay? But the tempting thing to do here is to use 22.4 liters per mole, but we cannot do that here because my pressure and temperature is not standard. Okay? So the first thing I have to do is I have to find the number of moles of oxygen. So we'll just list out the steps. Find moles of O2. So how are we going to do that? Hopefully, learning the last couple of videos, we can use the ideal gas law to do that. Okay, so if you want to write out PV equals nRT, that'll be great. So then, once we have the moles of oxygen, we can pretty easily find moles of CO2. Okay. Second step, we'll find moles of CO2. That should be a simple stoichiometry calculation. And then the last step is to find the volume of CO2. Okay. And we can take a shortcut for that because the problem says the CO2 is at STP. So if it's at STP, then I can just use 22.4 liters per mole there, make my life a lot easier. Okay. But we could potentially, if it weren't at STP, have to use the ideal gas law again to find the volume of CO2 present there. Okay? So let's go ahead and jump right in and do this. So the first step, find the number of moles of oxygen using the ideal gas law. So I have PV equals nRT. So I solve for N. So N equals PV over RT. I plug in my pressure is 2.26 atm. My volume is 55.8 milliliters, but we keep in mind that the units for my ideal gas constant are in liters, not milliliters. So it's very important here that you watch your units, and before you plug in, you have to go ahead and convert from milliliters to liters. So if you need to write that out, that's perfectly okay. Do a one-step dimensional analysis problem, but I'll just go ahead and write the answer in liters there. So I have 0.0558 liters divided by the ideal gas constant. So we have our pressure in atmospheres, so we can use 0.0821. So I have 0.0821 liters times atmospheres over mole times Kelvin times my temperature in Kelvin. So I cannot forget to convert my Celsius temperature to Kelvin there, and I get 313 Kelvin. Okay? So if you type that in the calculator, what you'll get is 0.0049, and then some more numbers, moles of O2. So rather than writing that number down and rounding it, just write down 0.0049, and I'll show you what we're going to do. So let me type it in. So I have 2.26 times 0.0558 divided by 0.0821 divided by 313. So that's what I get in the calculator. So I'm just going to write down 0.0049 moles of O2, but then I'm going to keep this number in the calculator, and then when I do my calculations with that number in a minute, I'm just going to keep this base number that I started with. That'll make my answer more accurate, and it will alleviate some of my rounding error issues I might potentially run into. So now that I have moles of O2, I can use stoichiometry to find moles of CO2. Okay, so I'm going to write 0.0049. I'll just write dot dot because I'm going to keep the number in the calculator. Moles of O2. So then I put moles of O2 down here, put moles of CO2 up here. So I go find my mole ratio. It is 2 to 3 from the balanced reaction. And then, rather than separating step 2 and step 3, I want to go ahead and do step 3 here, find the volume of CO2. Because the problem tells me it's measured at STP. So I know at STP there are 22.4 liters of CO2 and 1 mole of CO2. Okay? So it just saves me a step. If you want to break it up, you can, but I think when it says at STP, it's best just to go ahead and go all the way through it here. So now I still have this number in the calculator because I saved it. So I'll do times 2 times 22.4 divided by 3. So I want to round off to how many significant digits? Go back to the problem. 3 significant digits, 3 significant digits, 3. So I round off to 0.0733 liters, or I can write it as 73.3 milliliters of CO2. Sorry, my milliliters get a little bit messed up there. Okay. So none of the steps are difficult. You've already done all the steps before. We did the ideal gas law calculation in the last video. We've done stoichiometry before. The difficult part now is making our plan. Okay, so I think it's best on the side of your paper for every problem to write out your plan. Okay, that way you have steps on what to do. And go ahead and you can label these steps. So for step 1, you can write ideal ideal gas law. For this one, just write S for stoichiometry. For this one, just write 22.4 so you remember what to do. Okay, so that's the tricky part, is doing that. Okay, so now let's look at number 2, a very similar situation. Okay, so it gives you a little statement there, it gives you a reaction, and then it says if 285 grams of Fe3O4 are formed, what volume of hydrogen measured at 20.0 degrees Celsius and 1.06 atmospheres is produced. So here's a little bit different. So I start off with the mass of a solid. Okay, so the problem doesn't say it, but it should. Fe3O4 is a solid. Okay, so that's a little bit interesting. We have a solid, and we're trying to solve for a gas. Okay, so I can't really use the mass of a solid or the moles of a solid in the ideal gas law because that only applies to gases. So the first step is going to be to convert from grams of Fe3O4 into a more usable number. So we're trying to solve for volume of hydrogen, so let's decide really what value would be most helpful in allowing us to solve for the volume of hydrogen. Okay? Probably moles of hydrogen would be a good first step for us. So a good first step would be find moles of H2. How are we going to do that? We're going to use stoichiometry. Okay? So I can convert from grams of Fe3O4 to moles of H2. It's a good first step. Then once I have moles of H2, I can find volume of H2. And I can do that using the ideal gas law. PV equals nRT. Okay? So this is just really a 2-step problem. So there is no special formula or pattern for these problems. You just kind of have to apply what you've learned this semester and last semester to figure out the steps you need to take to solve these problems. So let's go ahead and dive right in and do this one. So I have 285 grams of Fe3O4. So 1 mole Fe3O4. Sorry, it's early in the morning when I'm recording this. I flipped it backwards. Let me get something to fix that. That's why you always go back and check your units, make sure they cancel. So hopefully you would have noticed that. Okay, so I want grams of Fe3O4 on the bottom. So then I have 1 mole of Fe3O4. I find the molar mass of Fe3O4 is 231.55 grams. Okay, you can double check me on that. So then I want to convert that to moles of H2. So 1 mole of Fe3O4 corresponds to 4 moles of H2. And that's just my mole ratio for my balanced reaction. I don't want to solve for grams of H2. I want to stop here with moles of H2, because moles of H2 is the number that I'm going to plug into my ideal gas law formula in a minute. Okay? So if we go ahead and type it in, we get 285 times 4 divided by 231.55. So we get, and I'll round it, 4.9 ... moles of H2. So just like before, I wrote down 4.9, but I'm going to hold this number in the calculator and save that for later. Okay? So now I come down here, that's my number of moles of H2. Now I can plug in the ideal gas law. So take a second to look at the problem and make sure you understand why in the previous problem I could use 22.4 versus why I have to use the ideal gas law here. We don't have standard temperature and pressure conditions. So I solve PV equals nRT for V equals nRT over P. Plug in my number of moles is 4.9 ... because I kept it in the calculator. Moles of H2. My ideal gas constant, I want my pressure is in atmospheres, so I'm going to use 0.0821 liters times atmospheres divided by mole Kelvin, times my temperature. I want to make sure that is in Kelvin here, so times 293 Kelvin divided by my pressure, which is 1.06 atm. Okay, so I check my units: moles, moles, Kelvin, Kelvin, atmospheres, atmospheres. I'm looking for volume. Liters did not cancel, so I'm in good shape there. So now I save that number in the calculator. Okay, so everybody, hopefully you can see that. So now I just finished typing the problem in: times 0.0821 times 293 divided by 1.06. Okay, and you get 111.7. Go back to the problem: 3 digits, 3 digits, 3 digits. So I round my answer to 3 significant digits. So I get 112 liters of H2. Okay. So again, hopefully the individual steps were not necessarily difficult for you. The only tricky part is figuring out when to do what. Okay. So we could have a situation where you have to do ideal gas law first, then stoichiometry. You could have a situation where you do stoichiometry first, then ideal gas law. There could be a situation where you have to do the ideal gas law, then stoichiometry, then the ideal gas law again. So if we look back at number 1, let's just, if we reworded this problem to say what volume of CO2 is produced when measured at 15 degrees Celsius and 1.5 atm. If we took away the standard temperature and pressure, we would have to do another ideal gas law calculation here instead of using 22.4. So there are several practice problems below. Looks like there are 3 through 8, so 1, 2, 3. There's 5 of these. They take a little bit of time, okay, but again, they're very important, okay. So make sure you can do these, go through, make sure your answer matches the one typed on the packet. And also, list out your steps to the side, okay. So if you email me and want me to check your work or something, ask me where you went wrong, the first thing I'm going to ask you for is where are your steps, what was your plan, okay. So always go into these with a plan, read the problem, think about it, decide what you want to do before you just start plugging in numbers and trying to calculate, okay. So go ahead and try those next few problems, make sure your answers match up. Hope you have a good rest of your day.